Here are the steps of bisection method. The first one, we're going to choose the lower XA and upper XB. Alright, so that these are the initial guesses that there is at least one root in between the interval of XA and XB, and the function changes sign over the interval. Okay, this can be checked by ensuring that the function evaluation fxa multiplied by the fxb must less than 0. The next step is to estimate of the root xm, okay, by half the root. So xm equals xa plus xb divided by 2. Okay, then step 3, we're going to evaluate the subinterval, okay, or the interval. Alright, if the function evaluation of fxa multiplied by fxm less than 0, then we can say that the root lies in the lower subinterval. Okay, so I can say that, if I can write it, the root lies in between the lower subinterval, which is in between the interval of xa and xm. If the multiplication fxa multiplied by fxm greater than 0, then you can say that the root lies in the upper subinterval. So the root lies in between xm and xb, upper subinterval. If fxa times fxm equals to 0, then we stop the iteration. We can say that the root equals xm. Okay, look at this example. Using the bisection method, find the root of fx equals to x to the power of 6 minus x minus 1 equals 0. And the error tolerance given is 0.001. Okay, and the initial guesses are given here, where the lower interval xa equals to 1 and the upper interval xb equals to 2. So we have to make sure that the function evaluation at this point, these 2 points, fxa multiplied by fxb must less than 0. So first we have to generate the table of bisection methods. We're going to have the column for n, the iteration, the column for the lower interval xa, the column for upper interval xb, the column for the midpoint xm, because we're going to halve the interval and the subinterval as iteration goes on. Okay, and then this is the function evaluation at the point fxa, and this is the function evaluation at the midpoint xm, and the last column is for the error. Okay, we're going to start with n equals to 1, the iteration, first iteration, xa equals to 1 and xb equals to 2. Okay, if we evaluate the function at the point xa and xb, so f1 is equals to minus 1, which is less than 0, and f2 is equals to 61, I think so, that is greater than 0. Okay, therefore we can say that f1 multiplied by f2 is less than 0. So therefore we can say that there is at least one root, okay, in between the interval 1, 2. Okay, the next step is to halve the interval 1 plus 2, 1 plus 2 divided by 2, then you get 1.5. So we have the midpoint in between 1, 2 is 1.5. Evaluate the function at the point xa and the point xm. Okay, then we get minus 1. Okay, then we evaluate the function at the midpoint. We substitute xm 1.5 into the function fx, then we get 8.8906. Okay, now we're going to evaluate the multiplication. Right, if we multiply fxa and fxm, so fxa multiplied by fxm, you can see that is less than 0 because minus 1 times 8.89 is minus value. Okay, basically I don't want to know the value, I just want to know the signs of the function evaluation. So it is acceptable if you just write down the sign without the value. Okay, so actually you can save time to evaluate the iterations, because you're going to have at least I think more than 4 or 5 iterations. Okay, you just need to write down the sign because we want to evaluate whether the multiplication is less than 0 or greater than 0. Now we can see that the function evaluation and the multiplication is less than 0. Therefore, in the next iteration, we're going to have new interval, which is the roots lies between the interval xa, xm, the lower subinterval. Because of the multiplication is less than 0, so we know that in between xa and xm, the root lies in between the interval xa and xm. Okay, now for the iteration 2, xa remains xa, while xb now is from xm. Okay, because from the first iteration, we know that the root lies between the lower subinterval, which is xa and xm. Okay, but before that, let's calculate the error. Okay, so the error is xb minus xm absolute. Okay, bear in mind the error always positive because of the absolute. So 2 minus 1.5 is 0.5. So the error is larger than error tolerance, so we have to proceed to the next iteration. So again, we do the same thing here. We're going to find the midpoint, evaluate the function at the point xa, evaluate the function at the point xm. Okay, find the error. Alright, now in the next iteration, iteration 2, okay, we halve the interval 1 plus 1.5 divided by 2, then you get 1.25. Okay, now we evaluate the function at the point xa and xm. Okay, what we got here is when evaluate the at the point xa equals to 1, you get minus 1. Okay, and the point 1.25, you get a positive value. Okay, alternatively, you just need to write down the sign only, minus, plus. Okay, so again, you can see that since the multiplication of fxa times fxm minus times a positive value, that is minus is less than 0. So therefore, in the next iteration, we should have the subinterval of the lower subinterval, which is xa remains 1, while xb now is 1.25. Alright, okay, then calculate the error. Okay, since we have the point, the interval, so therefore the error is half of the previous error. Okay, so you can see that this is 0.5 for the iteration 1, and the error for the iteration 2 is 0.25, where we halve the error. Okay, since we halve the interval, therefore we also halve the error. Okay, since in the iteration 2, fxa times fxm less than 0, therefore we're going to choose lower subinterval. So the new interval is xa remains xa 1, xb is equals to xm, which is 1.25. We repeat the process. Okay, we find the midpoint, then we get 1.125. Okay, evaluate the function at point xa, you get minus sign. At the point xm also you get minus sign. Alright, then calculate error. So as I mentioned just now, that we only need to halve the error in the previous iteration. So 0.25 divided by 2 is 0.125. Alright, so when we evaluate the multiplication of fxa and fxm is positive value, right? Minus is positive value. So therefore, the root lies in the upper subinterval. Alright, so in this iteration, for the next iteration, we're going to choose xb, xm. Sorry, is the other way around. Is xm xb. Alright, the upper subinterval. Okay, where the xa we change to xm and xb remains xb. Okay, we're going to repeat the process. Okay, now xa is equal to xm from the previous iteration. Okay, xb remains xb. Alright, okay, again half the interval, then you get 1.1875. Okay, evaluate the function at point xa xm and then find the error. Okay, you only need to halve the error, 0.125 divided by 2. Alright, so you can see that the evaluation at point xa minus sign, evaluation at the point xm is positive sign. So minus times positive is less than 0. Therefore, the root lies in the lower subinterval. Okay, the error is 0.0625. Then we're going to repeat the process. So here, just now we are at the iteration 4. So minus plus. Okay, minus is less than 0. Therefore, xa remains while xb is equals to xm. Okay, then we halve the point, the subinterval again. Alright, evaluate the function. Okay, as I mentioned to you guys, actually you don't have to write down the value. Okay, just need to write down the signs. It's acceptable. Okay, because we do not to worry about the value. We don't need to find the exact multiplication value. Alright, we just need to know the sign. Okay, then when you look at the error, okay, we only had, as I mentioned just now, you only need to halve the error until the error is greater or equals to the error tolerance 0.001. We have 10 iterations here. Then we're going to stop the iteration, terminate the computation. Okay, and the root is basically x, the roots. Okay, I put star to denote that it is the root of the nonlinear equation, approximation root. Okay, this is equals to 1.1338. We're going to choose the last value of xm in the last iteration. Okay, all right. Okay, that's all. Thank you.